Far beyond the shimmering veil of stars, visible to the naked eye, lies a realm where our understanding collapses under the weight of the unknown. A domain inhabited not by the well-lit celestial bodies we learn about in textbooks, but by mysterious, dark, and often undetectable world enigmatic planets that roam the cosmos without a sun, that bend the laws of gravity, or that lurk on the outermost edges of our solar system like silent sentinels watching from the void. These are not the planets you grew up with, the neat row of Mercury through Neptune orbiting obediently around our star. No. These are the rebels of the cosmic order, the invisible architects of gravitational whispers, and the hidden players in a universe far more complex than anyone dared imagine. And at the center of this intrigue sits the theoretical Planet X, sometimes called Planet 9, and conceptual bodies like Planet XB 9201, a symbolic vessel carrying our collective fascination with the unknown as it invites us to consider what else might be out there, circling the Sunday at distances so vast they stretch not just the fabric of our solar system, but the limits of our current physics and imagination alike. When scientists observed the unusual orbits of objects in the Kuiper Beltesy bodies lingering at the edge of Neptune's dominion, they didn't just shrug it off. Instead, their curiosity lit up with mathematical urgency, compelling them to propose a missing gravitational influence, a massive planet 5 to 10 times the mass of Earth, moving on an elongated orbit that could take as long as 20,000 years to complete a single revolution around the Sunday. And this wasn't mere speculation, but an inference drawn from Newtonian precision. A gravitational ghost logic told us must exist, even if no telescope had yet confirmed its presence. But the mystery didn't stop there. Beyond this hypothetical planet lies an entire category of celestial nomads, rogue planets, planetary bodies not anchored to any star, ejected during violent episodes of solar system formation, flung into the abyss where they now drift in eternal night, cold and silent, yet possibly brimming with secrets, as some theories propose that if they retained enough internal heat or possessed thick atmospheres of hydrogen, they might sustain subsurface oceans, and with that, the unthinkable possibility that life could exist even in the absence of starlight, shattering our heliocentric assumptions about the very requirements for biological existence. These thoughts are not idle science fiction fantasies, but real scientific considerations grounded in data, from microlensing observations that momentarily brighten background stars as a rogue planet passes in front, to infrared telescopes like WISE, and future missions like the Nancy Grace Roman Space Telescope, which will scan the darkness for the faintest thermal emissions, hoping to catch a whisper of warmth from these wandering giants that may outnumber the stars themselves. And yet, what we are truly hunting isn't just planets, it's a deeper understanding of the universe's architecture, the unseen scaffolding that holds everything in place, because these hidden planets might be keystones, silently orchestrating the orbits of smaller bodies, subtly reshaping our models of solar system formation, and even influencing our theories about how galaxies structure themselves through the elusive dance of dark matter, since any invisible mass that can warp gravity reminds us that what we see is but a fraction of what truly exists. In this light, the story of Planet XB 9201 becomes a metaphor, a symbol of our enduring pursuit to uncover that which lies just beyond reach, as we aim our instruments, run simulations, and comb through data for anomalies, searching not just for new celestial coordinates, but for new laws, new thresholds of understanding, new frameworks of reality itself. For every hidden planet we find or fail to find pulls on the thread of something deeper, questioning the limits of our knowledge, challenging our arrogance, and reminding us that we are still newcomers in a universe filled with secrets. Even the implications for extraterrestrial life take on new dimensions when considered through this lens. Because if planets without stars can remain geologically active for billions of years, warmed by tidal forces or radioactive decay, or protected by thick atmospheric blankets, then life, simple or complex, might be hiding in the most unexpected places. Not in the light, but in the cold. Not under blue skies, but beneath thick, icy shells or hydrogen seas. And the silence we hear might not be the absence of life, but the limits of our current detection methods, our instruments deaf to the quiet biological hum of alien ecosystems thriving in thermal vents far below frozen crusts. Furthermore, the existence of such planets raises profound questions about the origins of life itself. For if life can arise and endure on rogue planets or in the outskirts of stellar systems, then it may be far more common than we previously believed. Not a rare Earth miracle, but a cosmic pattern repeating itself across time and space. And this challenges us to rethink our definitions of habitability, to expand our search beyond the comfortable parameters of the habitable zone, and to ask whether biology is more versatile, more resilient, and more adventurous than our narrow earthbound experiences have led us to assume. Even from a philosophical standpoint, the notion of mysterious planets existing just beyond detection serves as a mirror to the human condition, where the most important truths are often hidden, not because they don't exist, but because we haven't yet developed the means to perceive them. And this makes the hunt for unseen worlds a deeply human endeavor, a blend of intellect and intuition, data and dreams, a testament to our refusal to accept the visible as the whole of reality. In many ways, our growing awareness of these enigmatic planetary bodies marks the beginning of a new era in space science, where exploration isn't limited by rocket trajectories or manned missions, but extends into the realm of deep analysis, mathematical modeling, and remote sensing technologies that allow us to map the invisible, to predict the existence of a planet from the way it tugs at distant rocks, and to simulate worlds so distant they may never be touched by human hands, yet still impact our understanding of everything from solar dynamics to the fate of life in the universe. With every step forward, we confront the humbling realization that we are still only scratching the surface of a cosmos vast beyond comprehension, layered with mysteries that defy simplistic answers. And in this light, the story of mysterious planets becomes not just a scientific journey, but a philosophical voyage, a quest to understand what kind of universe we live in and what kind of creatures we are to even dare ask such questions, to chase shadows across the sky, to believe that in darkness we might find not just cold, but meaning. For most of human history, the night sky was both a mystery and a map, a canvas filled with flickering lights that inspired mythology, fear, and wonder. Early humans gazed upward and saw divine stories etched in the stars, with constellations guiding agricultural cycles, religious practices, and navigation across vast oceans. In these ancient civilizations, Babylonian, Egyptian, Chinese, Mayan, Greek celestial bodies were often considered gods or messengers of fate, and their motions were recorded with astonishing accuracy despite the absence of modern instruments. The concept of a universe beyond Earth was virtually non-existent. The sky was seen as a fixed dome, with stars embedded like jewels in a celestial sphere. Earth stood at the center of everything, the unmoving foundation of existence, a belief formalized in the geocentric model championed by Claudius Ptolemy in the 2nd century CE. For over 1,000 years, this model dominated both scientific and theological thought, painting the cosmos as a series of nested spheres with Earth immovably at the center. But the seeds of revolution were slowly germinating, and in the 16th century, Nicolaus Copernicus dared to propose a heliocentric model, placing the Sunday, not Earth, at the center of the known universe. His work, published posthumously in 1543, did more than shift planetary positions. It challenged humanity's place in the cosmos, igniting a fire that would soon evolve into the scientific revolution. Galileo Galilei followed in the early 17th century with telescopic observations that forever altered our understanding. He discovered Jupiter's moons, proving not everything revolved around Earth, and observed phases of Venus that confirmed Copernican theory. Despite facing intense opposition from the Church, Galileo's evidence forced a re-evaluation of celestial mechanics and encouraged the emergence of empirical science. In the same century, Johannes Kepler formulated his 3 laws of planetary motion, showing that orbits were elliptical, not circular, and Isaac Newton built upon this foundation with his law of universal gravitation in the late 1600s, demonstrating that the same force governing an apple's fall also governed planetary motion. These breakthroughs linked heaven and earth with a common set of physical laws, dissolving the boundary between terrestrial and celestial realms, and laying the groundwork for classical mechanics. The Enlightenment further fueled this trajectory with a growing emphasis on reason, observation, and mathematics as the path to understanding the universe. But even with these massive strides, the universe remained relatively small in human minds' solar system, surrounded by a fixed shell of stars. It wasn't until the 20th century that our cosmic horizon expanded dramatically. In 1923, Edwin Hubble used the newly constructed Hooker telescope to resolve individual stars in the Andromeda Nebula, proving that it was not a cloud within our galaxy, but an entirely separate galaxy of its own. This was a seismic shift, revealing that the Milky Way was just one of countless galaxies floating in an expanding cosmic ocean. Shortly after, Hubble's observations of galactic redshifts led to the formulation of Hubble's law, establishing that the universe was expanding, a concept that would become central to the Big Bang theory. The idea that the universe had a beginning, a moment of creation from an extremely hot and dense point, emerged from the mathematical predictions of general relativity and the work of scientists like Georges Lemaitre and Alexander Friedmann. This was not merely a philosophical idea. It gained observational credibility in 1965, when Arno Penzias and Robert Wilson accidentally discovered the cosmic microwave background radiation, the afterglow of the Big Bang, which served as a fossil imprint of the universe's early conditions. Throughout the 20th century, physics and cosmology developed hand in hand, with quantum mechanics and Einstein's theory of general relativity offering the mathematical scaffolding to describe both the very small and the very large. The launch of Sputnik in 1957 by the Soviet Union marked the beginning of the space age, sparking a race that would culminate in the Apollo 11 moon landing in 1969, when Neil Armstrong stepped onto the lunar surface and made Earth's first mark on another celestial body. These moments transformed human consciousness, giving us not only new data, but a new perspective on where Earth was seen as a fragile blue dot suspended in the vast darkness, as captured in the iconic Earthrise and Pale Blue Dot images. Space exploration expanded further in the decades to come, with robotic missions to Mars, Venus, and the outer planets, deep space probes like Voyager 1 and 2 now traveling beyond the solar system, and telescopes like Hubble peering into the deepest regions of space and time. Meanwhile, on the theoretical front, new models emerged to explain the early universe and its large-scale structure, including the theory of cosmic inflation, which proposes a brief period of exponential expansion moments after the Big Bang, smoothing out the observable universe and solving several key cosmological puzzles. The concept of the observable universe itself became central to modern cosmology. Unlike earlier assumptions that the universe might be infinite and static, we now understand that the universe has a finite age, approximately 13.8 billion years, and because nothing can travel faster than light, we are limited in what we can observe. The observable universe is the spherical region of the cosmos from which light has had time to reach us since the Big Bang. Though the universe may be infinitely large, we are causally connected only to a portion of it, bounded by this cosmic horizon. Today, the observable universe contains an estimated 2 trillion galaxies, each with hundreds of billions of stars, and an even greater number of planets, moons, and asteroids. Despite this immensity, modern discoveries continue to challenge our assumptions. The detection of dark matter and dark energy, mysterious components that together make up about 95% of the total mass energy content of the universe, revealed how little we truly understand. Dark matter, inferred through gravitational effects on visible matter, and dark energy, discovered through the accelerating expansion of the universe, hint at deeper layers of reality still beyond our grasp. Particle physics also intersects with cosmology through efforts like the Large Hadron Collider, probing the fundamental building blocks of matter and the forces that governed the early universe, while missions like the James Webb Space Telescope promise to push the frontiers of observation, reaching back to the formation of the first stars and galaxies. Meanwhile, the study of exoplanets, planets orbiting other stars, exploded since the 1990s, with thousands of such worlds now confirmed, expanding our understanding of planetary systems and the potential for life beyond Earth. All of these discoveries and milestones have shaped an evolving cosmic narrative, one where humanity is no longer at the center, but is still deeply connected to the cosmos through shared elements, physical laws, and a common origin in the Big Bang. This journey from ancient myth to modern science illustrates not only the growth of human knowledge, but also the deepening of human humility, as we realize how vast, complex, and mysterious the universe truly is. And yet, even as we peer billions of light years into the past, we find that each answer uncovers more questions about the nature of time, the origins of space, the fate of the cosmos, and whether we are alone in its vastness. This relentless curiosity, driven by observation, mathematics, and the human imagination, continues to propel us forward, not only in our understanding of the universe, but in our quest to define our place within it. There's a moment, often in the stillness of night, when you look up at the sky and feel an overwhelming sensation that cannot be explained with facts or diagrams. A strange blend of awe and terror, of wonder and humility, as if the universe is whispering a truth too vast for language to hold. It is in this quiet confrontation with the cosmos that the most human of emotions emerge. Emotions that are older than science, older than myth, rooted in the deep, wordless parts of ourselves that have always yearned to understand, to find meaning in the patterns above. We care about the universe not because it offers easy answers, but because it reminds us how much we don't know. And in that mystery lies a kind of beauty that cuts through everything else. When we consider the possibility of hidden planets, of rogue worlds drifting in cold interstellar space, of galaxies colliding millions of light years away, or black holes devouring entire stars, we are not simply learning about space, we are confronting the infinite. And that confrontation reshapes us. The vastness of the universe forces us to reflect on our fragility, our brevity, our place in a drama so grand it defies comprehension. And yet, rather than feel insignificant, many of us feel inspired, as if being a small part of something so immense is its own kind of meaning, as if the stars themselves are inviting us to play a role in understanding them. The emotional pull of space isn't confined to scientists or astronomers. It touches children making their first paper rockets, dreamers staring into the dark sky from a quiet backyard, artists who paint nebulae with aching reverence, poets who write about the stars as if they were the soul's mirror. Even those with no interest in physics feel it when they watch a rocket launch or when they see images from the James Webb Space Telescope, revealing newborn galaxies from the dawn of time, glowing in colors that seem too sacred for human eyes. There's something almost spiritual in those moments, something that transcends the logic of numbers and calculations. It's the realization that we are part of a universe that creates stars in the silence, that sculpts planets from dust, and that, somehow, crafted minds like ours, minds capable of asking, why? We chase the cosmos because it calls to a deep need within us to know where we came from, why we exist, and what it all means. And no matter how advanced our science becomes, that emotional core never fades. In fact, it grows deeper, because the more we uncover, the more we realize how intricate, how delicate, how profoundly mysterious this universe truly is. There is fear too, and rightfully so. When we speak of black holes, we speak of regions where time and space are warped beyond recognition, where the known laws of physics collapse into singularity, and that can be terrifying. The idea that the Earth itself is just one rock orbiting a modest star in a remote part of an ordinary galaxy can provoke existential dread, a sense that we are floating in cosmic indifference, that nothing truly matters in the face of such scale. But this fear, this existential vertigo, is also what makes the journey worth it. Because to feel fear in the face of the cosmos is to be awake, to be alive to the full spectrum of human experience. It is a fear born not of ignorance, but of awareness. And in many ways, this fear is a gateway to deeper connection to each other, to our planet, to the fragile thread of consciousness that binds us across time and generations. We study the stars, not only to escape our smallness, but to understand it, to give it context, to transform it into something profound. When we discover planets beyond our solar system, some scorched and tidally locked, others shrouded in potential oceans, we're not just cataloging celestial bodies. We are imagining new homes. We are projecting ourselves into alien skies, wondering what it would feel like to stand beneath a triple-star sunrise, or to watch rings curve across the horizon of a distant world. These are not just data points. they are seeds of imagination, doorways into futures we haven't yet lived. For every exoplanet we detect, we ask again the timeless question, are we alone? And beneath that lies another, more personal question. If we are not alone, what does that mean for us? And if we are, then how precious is every life on this planet? How urgent is our need to preserve the beauty, the complexity, the miracle of Earth? In many ways, the universe is a mirror. It reflects our curiosity, our creativity, our courage to ask impossible questions. It doesn't owe us meaning, yet we can't help but search for it, driven by the same force that made our ancestors draw constellations in caves and erect monuments aligned with solstices. The wonder of the universe connects us across time, dissolving the illusion of separateness. It tells us that the atoms in our bodies were forged in ancient stars, that the calcium in our bones was once stardust, and that even as we live fleeting lives, we carry within us the memory of cosmic explosions and galactic births. That is not poetry, it is scientific fact. And yet it feels like poetry because it strikes a chord so deep we barely have words for it. We build telescopes not just to look outward, but to understand inward. We launch missions not only to explore Mars or Europa, but to expand the boundary of what's possible for human beings. The pursuit of space is the pursuit of ourselves. It challenges us to imagine more, to risk more, to dream on a planetary scale. It unites nations in shared curiosity as we pool our knowledge and resources to send probes beyond the solar wind or to map the background radiation of the Big Bang. And it also forces us to reckon with our limitations, our small-mindedness, our tendency to cling to comfort in the face of the unknown. But ultimately, it offers us a way out, not just a literal path to new worlds, but a philosophical path to perspective, humility, and hope. Even the concept of the observable universe, the idea that we can only see so far because light has a finite speed and the universe has a finite age, evokes a deeply emotional response. It reminds us that we live in a bubble of light, surrounded by a darkness we may never penetrate. And yet, we are constantly reaching beyond that limit, imagining what might lie just outside. That act of reaching is what makes us human. It is an act of defiance against the darkness, against entropy, against the silence. Every generation adds its own layer of understanding, building cathedrals of knowledge atop foundations laid by those who came before, not because we expect to finish the story, but because the story itself is worth telling. It is in that telling and that reaching that we find meaning. And for those who say the universe is too vast to matter, that our efforts are meaningless in the face of cosmic scale, consider this. The universe does not know that it is beautiful, or mysterious, or terrifying. It is we who give it those names. It is through human eyes that galaxies become art, through human minds that equations become gateways, through human hearts that stars become symbols of hope and memory. We may be small, but we are the universe made conscious, a brief spark of awareness capable of contemplating the infinite. That is not nothing. That is everything. In the end, we care about the universe because it reminds us what it means to be alive. It confronts us with our mortality and then offers us a kind of immortality, not through escape, but through understanding, through wonder, through the simple, radical act of asking questions that may never be answered. It tells us that we are part of something unimaginably large, and yet, in that largeness, we are not lost, we are found. Every glance into the night sky, every photograph of a distant world, every theory about the birth of time itself is a testament to our refusal to accept the limits imposed by fear or ignorance. It is our collective heartbeat echoing across light years. And that, more than any data point or formula, is why the cosmos matters. It is not just out there, it is in us, calling us to remember, to wonder, to reach. What if everything you've ever believed about the universe, about its size, its shape, its limits, was only a fraction of the truth? What if the most significant forces shaping your life aren't visible, not because they're too small to see, but because they exist on scales so large, so distant, or so strange that we've barely begun to recognize them? What if planets like Earth are not the rule but the exception? And out there in the cosmic dark rogue worlds drift silently through space with no star to orbit, each one potentially holding secrets that challenge everything we think we know about life, existence, and reality itself. And what does it mean that we are able to ask such questions at all? These are not idle curiosities or abstract puzzles. They are direct challenges to the very foundations of how we understand our place in the cosmos. Every time we uncover a new celestial body, every time we map a gravitational anomaly, every time we catch a glimmer of something that wasn't supposed to be there, we are forced to revise not just our scientific models, but our worldview, our philosophy, even our spiritual beliefs. Because in the end, space is not just out there, it's also inside us, reflected in our thoughts, our dreams, our myths, our ambitions. So ask yourself this: why do you care what lies beyond the stars? Why are you drawn to the night sky, to images of galaxies colliding, of exoplanets shrouded in clouds, of moons cracked with ice? Could it be because the mystery of the universe is also the mystery of you? The atoms in your body were born in ancient stars. The iron in your blood was forged in supernova explosions. You are not separate from the cosmos. You are its offspring, its expression, its voice. And yet, for all our modern knowledge, we still don't know how many planets are out there, how life began, why the universe expands, or what lies beyond the boundaries of what we can observe. We don't know what dark matter is, or what dark energy really does. We don't know if we are alone. Doesn't that excite you? Doesn't it terrify you? Shouldn't it make you want to ask more questions? To dig deeper? To keep looking? To keep wondering? The mystery of the universe is not a problem to be solved, but a journey to be experienced. It's not about having all the answers, it's about being awake enough to recognize the questions. New discoveries will not just fill in the blanks of our textbooks, they will rewrite the chapters entirely. Imagine finding a planet where the laws of physics behave differently, or discovering microbial life beneath the surface of a rogue planet with no sunlight. Imagine proving that the universe is only one of many, each with its own rules, its own histories, its own potential for life. What would that do to your understanding of reality? How would it change what you value, what you fear, what you hope for? If we found undeniable evidence of intelligent life elsewhere, would that unite humanity or divide it further? If we could see back to the first moment of time, would that make us feel closer to a divine origin or more disconnected than ever? Every telescope pointed at the stars is also a mirror held up to our civilization. The questions we ask about the universe reflect who we are, what we seek, what we fear. And those questions are evolving. Once we asked where the sun goes at night, then we asked what the stars are made of. Now we ask how many dimensions space might have, whether time had a beginning, and whether black holes are gateways to other realities. These aren't just scientific questions, they're philosophical, psychological, emotional. They reach into the core of identity. They challenge us to see ourselves as part of something unfathomably large and yet intimately connected. So here's another question for you. What would change in your life if you truly accepted that you are part of a living, evolving universe billions of years in the making? Would you act differently? Would you treat the earth with more reverence, knowing it's a rare jewel in a sea of darkness? Would you treat each other with more empathy, knowing we're all stardust walking and breathing and trying to make sense of the same mystery? This is why we must care, why we must engage, why the mysteries of space are not just the business of astronomers or physicists, but belong to all of us. Every time we ignore these questions, we shrink ourselves. Every time we engage with them, we expand. And you don't need a PhD to participate. You just need to be curious. You just need to ask, what if there are other forms of consciousness completely unlike our own, drifting through clouds of gas or pulsing in rhythms we cannot hear? What if time is not what we think it is, and the past and future are more connected than we realize? What if the universe itself is conscious, or if consciousness is a fundamental property of the cosmos like gravity or mass? What if we're only one evolutionary iteration in a long chain of cosmic intelligence, and somewhere out there, others are also looking up, wondering if they're alone? Think of what happens when a new exoplanet is discovered. Scientists model its atmosphere, estimate its mass, guess at its temperature. But then artists begin to paint it. Writers build stories around it. Musicians write songs inspired by the idea of alien skies. Children draw what they think the creatures might look like. That's the power of cosmic mystery. It infects every part of culture, of creativity, of emotion. It unites the analytical and the artistic. It sparks conversations between generations. It becomes something we share, something we care about, not just because it's cool or unknown, but because it gives us a reason to dream, a reason to reach, a reason to remember that we are still evolving, not just biologically, but mentally, spiritually, as a species trying to understand its origin and fate. So how can you be part of this journey? Start by staying curious. Question what you're told. Read articles. Watch documentaries. Discuss theories, not to win arguments, but to expand minds. Support space research. Follow missions. Let awe be part of your daily life. Talk about the universe with your children, with your friends, with people who think differently from you. Share the mystery. Don't wait for certainty to be inspired. Let the questions themselves be enough. Wonder is not weakness. It's a sign that you are still open, still growing, still alive to the possibility that there is more to this life than we know. In the years to come, we will discover more. New telescopes will pierce deeper into time. New missions will land on alien soil. AI will help us decode signals and spot patterns that once eluded the human eye. And in those discoveries will be new opportunities to reflect on who we are. Will we rise to the challenge? Will we see the universe not just as a frontier to conquer, but as a teacher, a mirror, a home we barely understand? Will we finally embrace the humility that comes from knowing how small we are and the responsibility that comes from knowing we are capable of understanding, of protecting, of honoring what little we can see? Your engagement matters. Your questions matter. Your wonder matters. Because the universe is not just a spectacle, it's an invitation. An invitation to think bigger, to feel deeper, to live with a sense of scale that stretches the boundaries of ego. So I ask you again, what does the universe mean to you? Not just the facts, not just the theories, but the feeling of it. The immensity, the mystery, the silence, the music, the fear, the hope, the beauty of not knowing, and the courage to ask anyway. This is your call to interaction, your call to wonder, because the mystery isn't going away. It's growing, and it's waiting for you. Imagine standing at the edge of a colossal void, a place where galaxies themselves are rare, where the density of matter is so low that light can travel for millions of years without touching anything. You float in silence, surrounded not by darkness, but by a kind of velvet absence, deeper than shadow, richer than black. In every direction stretches an incomprehensible ocean of space, dotted with glowing islands, galaxies so distant, their light began its journey before the Earth even formed. Each of these galaxies contains hundreds of billions of stars, each star potentially orbited by planets, moons, clouds of dust, and rings of ice. Some stars are newborn, burning with the fury of youth. Others are dying, collapsing inward to become white dwarfs or exploding outward as supernovae, scattering their elements into the galaxy like cosmic confetti. The atmosphere here is not breathable, not tangible. It is silence itself, broken only by the pulse of ancient light echoing from the edges of time. This is the universe we inhabit, even if we rarely feel it. A theater of gravity, energy, and time so vast that it bends imagination until it snaps, leaving us not with certainty, but with awe. A galaxy is not a simple structure. Spiral arms twist like celestial hurricanes, pulling stars, gas, and dust into graceful arcs that rotate around an invisible core. Some galaxies, like the Milky Way, are orderly, majestic spirals. Others are chaotic, stretched and warped by collisions with their neighbors. Between them lie intergalactic spaces vast enough to fit hundreds of galaxies, regions so empty that the average density is close to nothing. Yet even in the emptiness, mysteries linger. In some places, astronomers have found the Great Void, enormous cosmic gaps hundreds of millions of light years across, where few galaxies dare to exist. And then there are the cosmic filaments, the largest known structures in the universe, thread-like tendrils of galaxies stretching across the darkness, forming a kind of web. This is the large-scale structure of the universe, a sponge-like distribution where clusters of galaxies line up along filaments and surround voids, creating a texture that is both chaotic and beautiful. It looks almost alive. But even this visible universe, this grand ballet of light, is only part of the picture. The real puzzle lies in what we cannot see. When astronomers study the motion of galaxies, they find something strange. Galaxies spin too fast. Stars at their edges move as if pulled by a gravitational force that should not exist. They should fly apart, but they don't. The only explanation is that there is something invisible holding them together. This something is what we call dark matter. It does not emit light or energy. It does not reflect. It does not absorb. But it is there, detectable through its gravitational effects. Like a ghostly scaffolding, dark matter shapes galaxies, binds clusters, and threads the cosmic web. And it makes up about 27% of the universe. That's more than all the atoms, all the stars, all the planets combined. And still, dark matter is only part of the unknown. In the late 1990s, scientists measuring the expansion of the universe discovered that it was not slowing down due to gravity. As expected, it was accelerating. Some form of energy, was pushing the universe apart, counteracting gravity on the largest scales. This force, now called dark energy, makes up nearly 70% of the universe. We don't know what it is. We don't know why it exists. But we know it is causing space itself to stretch faster and faster. Together, dark matter and dark energy account for 95% of everything. And yet, they remain invisible, unknowable, a constant reminder that the universe is not just larger than we imagine it, is stranger than we can imagine. The key players in the field of cosmology are not only the forces and phenomena themselves, but also the brilliant minds who dared to chase them. Albert Einstein reshaped our understanding of gravity with his theory of general relativity, showing that mass bends space and time, creating what we feel as gravity. His equations predicted the expansion of the universe before anyone observed it. Edwin Hubble confirmed that expansion by observing distant galaxies moving away from us. The farther they are, the faster they flee. Georges Lemaitre, a Belgian priest and physicist, proposed the idea of a primeval atom, the precursor to what we now call the Big Bang. Vera Rubin provided the critical evidence for dark matter, observing that the rotation curves of galaxies couldn't be explained without an invisible mass. Alan Guth introduced the theory of cosmic inflation, suggesting that the universe expanded faster than the speed of light in its first fractions of a second, solving long-standing cosmological puzzles. And more recently, scientists like Saul Perlmutter and Adam Riess discovered the accelerating universe, using distant supernovae as standard candles to map cosmic expansion. But the tone of modern cosmology is not triumphant. It is humble. It is haunted by questions. What happened before the Big Bang, or does that question even make sense? Are there other universes, each with different laws of physics, arising from a multiverse of quantum possibilities? What is time, really? Why does the universe have the structure it does? Why are the constants of nature so finely tuned for life? These questions are not limited to chalkboards or observatories. They bleed into philosophy, into theology, into the human experience itself. And in their pursuit, scientists are not chasing facts alone. They are seeking meaning. The tone is one of reverent curiosity, a willingness to ask the unanswerable, to stand in the presence of something infinitely vast and say, "I do not understand, but I want to try." Our instruments are becoming extensions of our senses, allowing us to see the invisible and hear the silent. The Hubble Space Telescope showed us the deep field, revealing thousands of galaxies in a tiny patch of sky no bigger than a grain of sand held at arm's length. The James Webb Space Telescope goes even further, capturing light from the first galaxies ever formed, their glow stretched into the infrared by billions of years of expansion. Meanwhile, gravitational wave detectors like LIGO and Virgo have opened a new sense zone that listens for ripples in space-time itself, created when black holes collide or neutron stars merge. Each discovery adds a layer to our understanding, a note to the symphony of the cosmos, a whisper from the deep past. Even black holes, once theoretical curiosities, have become real, observed, photographed. The Event Horizon Telescope produced the first image of a black hole in 2019. Capturing the shadow cast by its event horizon, against the glowing plasma surrounding it. It looked like a cosmic eye staring back at us. In its simplicity and mystery, it became an icon of the unknown, a reminder that the universe hides more than it reveals, but also that we are capable of peeking behind the curtain, however briefly. The setting is immersive not because of any special effect, but because of what it evokes in the mind. There are places in the universe where stars form in colossal nurseries of gas and dust, collapsing under their own gravity until nuclear fusion ignites. There are planets orbiting dead stars, tidal locked to one hemisphere of eternal day and the other of eternal night. There are neutron stars no wider than a city but heavier than the sunday, spinning hundreds of times per second, emitting beams of radiation like cosmic lighthouses. There are quasar-sangent galaxies with cores so bright they outshine the galaxies themselves, powered by supermassive black holes, devouring matter at breakneck speeds. There are gamma-ray bursts, the most powerful explosions since the Big Bang, lighting up the cosmos with terrifying energy. And then, there is the cosmic microwave background, a whisper of the universe's first light, frozen into the fabric of space like a photograph of time's birth. To enter this setting is to be transformed. The awe is not performative, it is real. It strikes suddenly, like a realization you didn't know you were waiting for. It comes when you learn that the universe has no center, that the Big Bang happened everywhere at once, that space itself is expanding, not into anything, but creating more space as it grows. It comes when you understand that time is not absolute, that your experience of reality is shaped by your motion, your gravity, your proximity to mass. It comes when you realize that we are the first known creatures in the universe who can ask what the universe is. That alone is worthy of reverence. And yet, the tone is never static. It shifts between awe and urgency, between humility and hunger, between stillness and the frantic pace of discovery. Scientists are in a race not just against each other, but against the limitations of their instruments, the biases of their models, the shortness of their own lives. The data we gather today may not be understood for decades. The questions we ask now may not be answered in this century, but the act of asking, the act of exploring, the act of building telescopes and colliders and probes and theorises, an act of hope. It is the hope that we are not just observing the universe, but participating in it, becoming a more self-aware part of the cosmos through each generation of knowledge. So let yourself be immersed. Picture yourself not just in space, but as space. You are made of atoms formed in dying stars. You are organized by laws that apply across billions of light years. Your consciousness is a flicker in the long timeline of the universe, but a flicker bright enough to wonder why the timeline exists at all. You are the universe asking about itself. And that makes the cosmic setting not distant, but intimate. Not foreign, but familiar. Not empty, but full of potential. You are not just in the atmosphere of the universe, you are the atmosphere. You are the voice. You are the question. And you are only just beginning to ask. As we push further into the frontier of space, with instruments that can peer billions of light years into the past, and theories that stretch beyond the birth of time itself, there is a creeping realization threading through the heart of modern cosmology: attention, a conflict that we may never fully resolve. For every answer we find, new questions emerge, like hydra heads, more complex, more abstract, and more elusive than before. We begin to see that the edge we're searching for, the final boundary of understanding, the ultimate answer to how the universe began, what it's made of, and where it ends may always remain just out of reach. The very structure of the cosmos seems to conspire against our desire for closure. The universe is expanding faster than we can observe it. Galaxies are disappearing beyond our cosmic horizon, and the observable universe itself is not a fixed stage, but a dynamic, shrinking window on a reality that is drifting away from us. We are trapped in a sphere defined not by distance, but by time, and speed. Light can only travel so far in the age of the universe. And so beyond that sphere, we cannot see. But more than that, we cannot know. The fundamental nature of reality might exist in regions forever causally disconnected from us. This isn't just a practical limit. It's a philosophical one, and it may be the greatest wall human curiosity will ever face. Even within our accessible universe, paradoxes lurk. Physics, the most precise language we've ever created to describe the cosmos, begins to fray at the edges. General relativity, our best theory of gravity, which predicts black holes and explains the shape of galaxies, collapses into meaninglessness at the singularity, the core of black holes, and the theoretical starting point of the Big Bang. There, equations yield infinities, and space-time folds into a question mark. At the smallest scales, quantum mechanics reigns, a theory as bizarre as it is successful, where particles exist in many states at once, and nothing is determined until it is measured. And yet, we still have no consistent way of merging these two giants, relativity and quantum theory, into a unified framework. The search for quantum gravity, string theory, or loop quantum gravity continues. But each approach reveals more assumptions, more untested dimensions, more mathematical scaffolding, with less and less observational grounding. We are confronted with theories so complex, so detached from experimental verification, that they begin to feel more like metaphysical speculation than science as we know it. Are we inventing explanations that cannot be proven? Are we chasing shadows in an infinite hall of mirrors? Then there are the cosmological puzzles that mock our current understanding. The cosmic microwave background, that ancient light from when the universe was only 380,000 years old, is astonishingly smooth, far smoother than it should be, given the vastness of space it spans. Inflation theory was proposed to explain this, positing that the universe underwent a burst of exponential expansion moments after the Big Bang, stretching quantum fluctuations into the seeds of galaxies. It fits the data beautifully, but it raises further questions. What powered inflation? Why did it stop? Could it happen again? And if inflation is real, it may imply something even more unsettling, that our universe is just one bubble in a vast eternal multiverse, where each pocket universe has its own physical laws, constants, and histories. If this is true, then the quest for a theory of everything may be misguided, because there may be no single, unique framework that explains it, only an infinite variety of universes, each internally consistent but mutually inaccessible. In such a scenario, our universe becomes a local anomaly, and deeper truths remain buried forever in realms we can never reach. The limitations are not only theoretical, but also technological and observational. As we look deeper into the universe, we are looking back in time, but we cannot see before the cosmic microwave backgrounded is a wall of opacity, a time when the universe was too hot and dense for light to move freely. Anything that happened before that, during inflation or the Planck race, hidden from direct observation, we can only infer, simulate, or speculate. Our best detectors, like the James Webb Space Telescope, may see the first stars, but not the moment of origin. Our instruments have quantum limits, thermal noise, calibration drift. We are mapping the shadows of reality, not the reality itself. Even the most advanced missions are shaped by human bias: what we expect to find, what we choose to measure, how we interpret the data. The very act of observation is bounded by our biology, our mathematics, our cognitive tools. And as we reach further, the noise grows louder, the signals weaker, the questions more entangled with uncertainty. Moreover, the universe itself is not static. As space expands, it carries galaxies away faster than the speed of light, not because they are moving through space, but because space itself is stretching. This means that more and more of the universe is slipping beyond our observational horizon. A future astronomer, billions of years from now, may look into the sky and see only emptiness, unaware that there was ever a cosmic web, ever a Big Bang, ever anything beyond their own isolated galaxy. In that sense, we are living in a golden age of cosmological observation, where the past is still visible, but fading, like a cosmic sunset. Our descendants may inherit a darker sky, not because the universe died, but because its story drifted out of view. We are privileged observers of a fragile, temporary window into the deepest history of time. And even now, we may be missing pieces too faint, too strange, or too far to detect. And then, there are the paradoxes that challenge not just observation, but logic itself. The black hole information paradox, for instance, pits quantum mechanics against general relativity. If nothing can escape a black hole, and if matter falling into it carries quantum information, then when the black hole evaporates via Hawking radiation, where does that information go? Quantum theory says information cannot be destroyed, but relativity says it disappears into the singularity. New theories suggest information may be encoded in the event horizon, or perhaps leaked out slowly, but none of these ideas are yet conclusive. Each proposed resolution introduces its own complications, raising more foundational questions than it settles. Or, consider the measurement problem in quantum mechanics. Does a particle exist in multiple states until someone observes it? Does reality depend on observation? Is consciousness necessary to collapse the wave function? These are not questions we can answer with bigger telescopes or more sensitive instruments. They are cracks in the foundation of knowledge itself, suggesting that the universe may be more participatory than passive, more entangled with mind and meaning than we previously believed. Our understanding is challenged not just by the vastness of what we do not know, but by the shifting nature of what we think we do know. Scientific progress is not a straight line. It is a spiral of revision, falsification, refinement, and sometimes complete paradigm shifts. Newton's universe gave way to Einstein's. The steady-state model gave way to the Big Bang. The certainty of classical mechanics collapsed into the probability clouds of quantum theory. Even now, dark matter and dark energy dominate our equations but elude our understanding. Are they real substances, or signs that gravity itself behaves differently on cosmic scales? Modified Newtonian dynamics, MOD, emergent gravity, quintessence. Each offers a radical alternative. Each is partially right, and none are complete. The theories change, the observations improve, but the questions remain and they multiply. We may never find the edge, not because it doesn't exist, but because it keeps moving. Like the horizon on a ship at sea, it recedes as we approach it. Each new discovery opens a door to a deeper mystery. The structure of atoms revealed the quantum world. The study of galaxies revealed dark matter. The measurement of cosmic acceleration revealed dark energy. And beyond them, the multiverse, the holographic principle, simulated realities, and other ideas that stretch even the definitions of science. It's not just that we don't have all the answers. It's that we may be fundamentally incapable of having them. Our minds evolved to hunt, to build, to love, and not to comprehend infinite dimensions, nonlinear time, or realities where cause and effect dissolve. Yet we continue. We build bigger colliders. We launch deeper space missions. We train AI to recognize patterns in the noise. We write equations in the language of symmetry and geometry, hoping the universe still speaks it. We stare into black holes. We map the cosmic microwave background with precision that rivals any human endeavor. We simulate universes in supercomputers. We debate fine-tuning and entropy. We hypothesize about bubble collisions in the multiverse and the entropy of time. We theorize about pre-Big Bang physics and space-time loops. We are not content with partial truths, even if full truth may be unreachable. And maybe that is the conflict itself. Not the battle between science and ignorance, but between human curiosity and cosmic indifference. The universe does not promise answers. It does not guarantee coherence. It offers clues, fragments, riddles. It rewards patience, humility, imagination. It punishes certainty and arrogance. It reminds us always that we are not its masters, we are its children, made of its dust, shaped by its laws, bound by its horizons. And yet, for reasons we don't fully understand, we are the only known part of it capable of asking why. The deeper we go, the less we know, and the more we realize how much more there is to not know. Perhaps that is the lesson, that the edge is not a place, but a process. Not a line, but a question. Not a destination, but a pursuit. We may never find the edge, but in searching for it, we find ourselves. We find meaning. We find a reason to keep looking. And that, perhaps, is the only truth that matters. The heart of modern cosmology pulses with tension, not between scientists and the unknown, but between the very theories scientists themselves propose to explain it. The universe, once thought to be a static, harmonious machine governed by elegant, universal laws, is now understood to be a place of paradoxes, mismatches, and unresolved contradictions. Beneath the polished surface of documentaries and clean-cut equations lies a quiet but relentless conflict, not just about what the universe is, but what it means for something to be knowable at all. This conflict is perhaps most evident in the attempt to define the very shape, size, and edge of the universe. For centuries, Science was on a quest to draw a map of the cosmos, to define its boundaries, to measure its contents. And in many ways, we succeeded until we didn't. Because the more accurately we observed, the less certain we became. The further we extended our reach, the more the lines began to blur. And now, standing at the edge of knowledge, cosmologists find themselves staring into a rift between observation and theory, between competing models that cannot all be true. One of the oldest and most persistent tensions lies in the question of whether the universe is finite or infinite. The idea of an infinite universe has long been troubling. It suggests no center, no boundary, no limit. It stretches the human mind past breaking. If the universe is infinite, then anything that can happen will happen, somewhere, sometime, an infinite number of times. There would be other Earths, other yous, other histories playing out in endless variation. But an infinite universe also raises mathematical and physical nightmares. How do you define total energy in an infinite space? How do you describe causality or entropy? Does time itself loop? And then there is the philosophical weight. What does it mean to be unique, to make choices, in a reality where every possibility is already realized? On the other hand, a finite universe is more palatable. It can be measured, bounded, perhaps even visualized. But then comes the problem. What lies beyond its boundary? Is there an outside to space? Is space curved in on itself like the surface of a spheriphenite but unbounded? Or is it closed off by something we cannot perceive, hidden behind the limitations of observation? The struggle intensifies when we add in the concept of the observable universe. What we see, what we can ever seize, defined not by the extent of the cosmos itself, but by the speed of light and the age of the universe. Light takes time to travel, and the universe is 13.8 billion years old. But due to cosmic expansion, the observable universe extends much further, about 93 billion light-years in diameter. Anything beyond that horizon is, in theory, forever out of reach. But is the universe itself larger than this? Most physicists believe it is possibly infinitely larger, but we have no way to test this. Theories diverge. Some models suggest a finite but unobservable boundary. Others propose a multiverse, a mosaic of bubble universes beyond our own, each with different physical constants, unreachable by any means. And while these models are mathematically valid, they provoke intense disagreement among scientists. Can we call something science if it is, in principle, untestable? Do we need empirical data, or is internal consistency enough? That's the clash at the core of this conflict. On one side, we have the theorists developing complex models built on deep mathematics, string theory, brain cosmology, eternal inflation, the holographic principle. These frameworks offer elegance and scope. They attempt to unify gravity and quantum mechanics, to explain dark energy, to trace the origin of time. But most of them remain untested, perhaps untestable. They rely on higher dimensions, on energies we can't access, on patterns we can't yet detect. On the other side stand the observational cosmologists, grounded in data. They map the cosmic microwave background, chart the redshifts of galaxies, measure dark energy with type Ia supernovae. Their tools are rooted in instruments and numbers, in what we can see and test. And while they rely on theory to interpret that data, they often find themselves constrained by its assumptions. This creates tension not just between camps of researchers, but within the very practice of cosmology. Theories like cosmic inflation explain the smoothness and flatness of the universe, the uniformity of the CMB, the distribution of galaxies. But inflation also predicts a multiverse concept for which there is no observational support. Does that make it unscientific? Or is it a consequence we must accept, even if we can't test it? And what about dark matter and dark energy? They were invented to explain discrepancies in observation, missing mass, accelerating expansion. But after decades, we still have not detected dark matter directly, nor do we understand the mechanism behind dark energy. Are we describing real substances, or are we patching our theories to fit the data? Competing explanations often arise from the same data. For example, the rotation curves of galaxies suggest that there is more mass than we can see. One explanation is dark matter. Another is modified Newtonian dynamics. MUND, which tweaks the laws of gravity at very low accelerations. MUND works surprisingly well in some cases, better than dark matter in predicting galaxy behavior. But it struggles to explain larger-scale structures like galaxy clusters and the CMB. Dark matter, by contrast, fits the large-scale models, but fails in the fine detail. Neither theory is complete. Both are flawed. And yet they continue to compete, dividing the community, each with passionate defenders and fierce skeptics. There is also conflict around the interpretation of time and space themselves. Einstein's relativity shows that time is not absolute, is relative to motion and gravity. But quantum mechanics assumes a universal clock, a shared now. This tension explodes when we try to build a theory of quantum gravity. Time becomes emergent, space becomes discrete, causality breaks down. In some models, the universe has no beginning. In others, time loops back on itself. In yet others, the universe is a hologram, and space is an illusion. These are not metaphors, they are serious theoretical proposals. But which is right, and how would we know? Perhaps the most profound conflict lies in the nature of reality itself. Classical science assumed that the universe was out there, an objective reality, governed by laws, discoverable through observation. But quantum theory undermines this. The act of measurement alters the system. Particles behave like waves until observed. Reality seems to choose its state when we look. This leads to interpretations like the Copenhagen interpretation, which denies any underlying reality until observation, and the many worlds interpretation, which posits infinite parallel universes to account for every quantum choice. Neither has empirical superiority. Both are philosophically unsettling, and both hint that our traditional ways of knowing may be inadequate for the task of understanding the cosmos. In this storm of competing frameworks, cosmologists find themselves not only debating the universe, but also redefining science itself. Is it enough for a theory to be mathematically elegant? Must it be testable? Falsifiable? Predictive? What do we do when our instruments reach their limits? When the data we need lies behind an event horizon or beyond the speed of light? Do we abandon those questions? Or do we invent new forms of inquiry, new definitions of science, new tools that transcend current limitations? Even the public perception of science is touched by this conflict. People want answers, clear, definitive truths about the cosmos. But cosmology offers uncertainties, probabilities, competing models. It offers beauty, yes, but also ambiguity. Scientists are asked to explain why the universe exists, why it looks the way it does, what happened before the Big Bang. And often, the honest answer is, we don't know. Or worse, we may never know. Yet perhaps this is not a failure. Perhaps this conflict is the essence of science at its best, not a clean consensus, but a vibrant argument, not a final truth, but a living process. Each model, each theory, each measurement is a step, not a destination. And in that struggle between observation and imagination, between data and dream, we create something greater than certainty. We create understanding, provisional, imperfect, ever-evolving understanding. The universe does not yield its secrets easily. It resists simplicity. It demands humility. And in that resistance, we are made stronger, sharper, more curious. We are forced to rethink our assumptions, to challenge our frameworks, to reinvent our very questions. The universe, after all, is not obligated to make sense to us, but we are obligated to try. And it is in that trying, in the clash of theories, the tension of models, the creative friction of ideas, that cosmology finds its deepest purpose. The edge may remain undefined, the conflict may never be resolved, but through it we come closer to the truth, not as a final answer, but as an ever-deepening mystery. And in that mystery, we find not despair, but meaning, not chaos, but a new kind of order, one that honors the complexity of the cosmos and the relentless curiosity of the human mind. What if the universe has no edge? What if space goes on forever? Not in a loop, not in a curve, but endlessly, directionless, borderless, with no final wall, no cosmic barrier, no signpost that reads, "Here ends everything"? This idea is not just a hypothesis, is one of the leading possibilities in modern cosmology. And yet, even as it quietly sits within the equations of general relativity and in the interpretations of the cosmic microwave background, it carries profound consequences, not just for physics, but for our very way of thinking. If the universe has no edge, then it has no center either, no privileged vantage point, no place of origin in the spatial sense. The Big Bang did not happen at a point, but everywhere at once. Space itself was born in that moment, and it has been expanding not into pre-existing emptiness, but creating new space-time as it grows. This means there is no outside, no perimeter, no edge to reach. And for the curious human mind, wired to explore, to map, to finish the puzzle with that last missing piece, this is a deeply destabilizing concept. It suggests a cosmos with no final destination, only infinite continuation. It replaces the comfort of boundaries with the vertigo of endlessness. And in doing so, it forces a reckoning with everything we think we know about existence, meaning, and knowledge itself. From a purely physical standpoint, a universe with no edge challenges many of our intuitions about measurement, containment, and energy. In a finite space, you can speak of total volume, of total mass, of entropy contained within defined limits. But in an infinite universe, those values become undefined or divergent. How do you talk about average density in a space where volume goes to infinity? How do you calculate probability when all outcomes are repeated an infinite number of times? The implications for cosmology are staggering. In an infinite universe, the notion of uniqueness begins to dissolve. Every arrangement of matter, every possible history, every quantum configuration would occur not just once, but countless times. Somewhere, in a region too far away to observe, there could be another Earth, another solar system, another version of you reading this exact sentence. These duplicates wouldn't be magical. They'd be statistical inevitabilities, born from the endless roll of quantum dice across limitless cosmic space. This forces cosmologists to confront a fundamental paradox. How do we make scientific predictions in a universe where everything that can happen does happen? Probability itself begins to collapse under the weight of infinity. If every event occurs an infinite number of times, then no event is more likely than another in the traditional sense. And yet, we experience a highly ordered universe with regular laws, consistent observations, and coherent structure. Why? This tension leads to one of the most profound consequences of the conflict: the realization that our existing models of physics, beautiful and successful as they are, may be incomplete or even fundamentally incapable of describing ultimate reality. General relativity explains the large-scale structure of space and time. Quantum mechanics governs the subatomic world. Both work extraordinarily well within their domains. But where they meet inside black holes, at the origin of the universe, they clash. They speak different languages, follow different rules. Their equations diverge. And the result is not merely a failure of calculation, it is a sign that our understanding of space, time, energy, and causality is deeply fractured. If the universe has no edge, and if our best models break down at its most extreme points, then we are left with two possibilities. Either we accept the limitations of our knowledge and redefine science as a probabilistic local endeavor, or we develop new physics. Physics that transcends our current frameworks, that unifies the laws of the cosmos into a deeper, more general theory, one that can handle infinities not as breakdowns, but as features. This is where quantum gravity, string theory, and loop quantum gravity enter the scene. These are not just exotic mathematical playgrounds. They are urgent attempts to reconcile the infinite and the finite, the continuous and the discrete, the local and the global. They aim to describe space-time as something emergent, not fundamental, to show how the universe might arise from a deeper level of reality where traditional notions of space and time no longer apply. But despite decades of research, no single model has emerged as definitive. We are still in the dark, still guessing, still piecing together fragments of a picture too vast to see all at once. The philosophical consequences are just as dramatic. If there is no edge, then the universe has no boundary condition. If it is infinite, then it was never meant to be grasped in the way we grasp a machine or a system. It simply is. And that isness, that boundless presence, collides with our deepest need for narrative, for enclosure, for meaning. Human beings are storytellers. We want beginnings, middles, and ends. We want structure. But the universe may offer none of these. It may be eternal, without cause, without purpose, without teleology. It may be a brute fact and chosen, unplanned, unguided. And if so, what does that mean for us? For our values, our aspirations, our sense of identity? Are we simply an accident? A fleeting configuration of matter in a sea of randomness? Or does the very act of wondering give us a kind of significance, even if the cosmos itself is silent? The existential impact of a boundless universe is profound. It replaces the comforting image of a watchmaker universe, a designed, finite system, with a far stranger reality, one where even the question, "Why are we here?" may be unanswerable. Not because the answer is hidden, but because it may not exist at all. And yet, within this disorienting vastness, many find a new kind of meaning, not derived from purpose, but from participation. If we are made of stars, if our consciousness is an emergent property of cosmic dust following universal laws, then to exist at all is a miracle of complexity. To ask questions is to bring awareness into the void. To seek understanding is to continue the universe's own unfolding. And in that, there is a kind of grace, not the grace of certainty, but the grace of curiosity, of humility, of knowing that we are small, but not insignificant. Still, for science to proceed, it must grapple with these consequences. It must learn to operate without final boundaries. It must create models that are robust in the face of infinity, theories that can explain not only what we observe, but why we observe this and not something else. The anthropic principle is one such attempt, suggesting that the universe appears fine-tuned for life because only in such a universe could beings like us exist to notice. But this is not a satisfying answer for many. It feels tautological, circular, even lazy. And yet, in a multiverse where all possibilities are realized, it may be the only explanation left. The challenge, then, is to find ways of testing these ideas, of moving beyond philosophy and into falsifiable science. Can we find signatures of other universes in the cosmic microwave background? Can we detect variations in physical constants across space? Can we build mathematical frameworks that reduce to our known laws in the appropriate limits? The need for new physics is urgent, not because our current models are wrong, they work spectacularly well, but because they are incomplete. They cannot explain dark matter. They cannot explain dark energy. They cannot resolve the singularities at the heart of black holes or the beginning of time. They cannot unify the four fundamental forces of nature. They cannot tell us whether space is continuous or quantized, whether time flows or emerges. They cannot answer the biggest question of all: why is there something rather than nothing? And so we push forward. We build bigger particle colliders, launch more sensitive telescopes, develop more powerful algorithms. We explore not just the universe, but the foundations of knowledge itself. We imagine alternate geometries, hidden dimensions, emergent symmetries. We search for the edge, even if it does not exist, not because we expect to find it, but because the search itself is what defines us. A universe without edge is not a failure, it is a challenge. It invites a different kind of understanding, one that is probabilistic rather than deterministic, open-ended rather than closed, participatory rather than observational. It invites us to redefine our relationship with knowledge, with truth, with reality itself. And in that redefinition, we may find something even more profound than final answers. We may find a new humility, a new curiosity, a new way of being. For in the end, the consequences of the conflict are not the dissolution of science, but its transformation. A recognition that the cosmos is not a puzzle to be solved, but a mystery to be lived, that the journey matters more than the destination, that in asking, in seeking, in wondering, we become not just students of the universe, but part of its story. There are moments in the history of science that redefine not just what we know, but how we know. They are turning points, disruptive revelations that alter the course of inquiry, force the rewriting of textbooks, and shift our collective imagination about what the universe is and what it could be. In cosmology, the science of the universe as a whole, The turning point came not in a single experiment, but through a series of breakthroughs, each sharpening the image of a cosmos far more dynamic, strange, and expansive than anyone had predicted. Where once the universe was assumed to be static, finite, and comfortably familiar, modern discoveries have unveiled a reality in constant motion, guided by forces invisible to the eye and ideas that stretch the limits of comprehension. This shift began subtly, with careful measurements, but it culminated in a revolutionary realization. Not only is the universe expanding, it's accelerating, and the force behind that acceleration, now called dark energy, may be the most powerful and mysterious component of reality. For much of the 20th century, the idea that the universe is expanding was already a radical departure from centuries of thought. The work of Edwin Hubble in the 1920s, showing that galaxies were moving away from us, and that the farther they were, the faster they receded, shattered the old notion of a static universe. This expansion was taken as evidence of the Big Bang moment, when all space, time, matter, and energy emerged from a hot, dense state and began to evolve. For decades, cosmologists assumed that gravity would act as a braking force, slowing the expansion over time. The central debate was whether the universe would eventually stop expanding and collapse back into a big crunch, or whether it would keep expanding forever at a slower and slower rate. But in the late 1990s, two independent teams of astronomers, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Riess, were using distant Type Ia supernovae as standard candles to measure the rate of cosmic expansion. Their goal was to determine whether the expansion was slowing down or plateauing. What they found, instead, shocked the scientific community. The expansion of the universe was not decelerating, was speeding up. This discovery was completely unexpected. It implied that some previously unknown form of energy was permeating all of space and pushing it apart with increasing force. This energy, dubbed dark energy, now appears to constitute nearly 70% of the total mass energy content of the universe. It does not clump like matter. It does not dilute as space expands. It behaves more like a property of space itself, an inherent pressure that grows as the cosmos stretches. The implications of this revelation cannot be overstated. Dark energy not only dictates the future of the universe, it redefines our understanding of its present structure. If the acceleration continues, galaxies will eventually recede so quickly that their light will no longer reach us. The observable universe will shrink, not because the universe itself is getting smaller, but because more of it is moving beyond our ability to detect it. Civilizations billions of years from now might live in apparent solitude, unaware that the cosmos once teemed with galaxies. More urgently, dark energy challenges our most cherished theories of physics. It doesn't fit neatly into the standard model of particle physics. It resists explanation through Einstein's general relativity. It demands either the existence of a cosmological constant, as Einstein once proposed and then discarded, or the invention of new fields, new particles, or even new dimensions of space. This turning point, this confrontation with a cosmic force we cannot see, but that governs everything, has energized cosmology like never before. And it has been accompanied by another revolution, a leap in our technological ability to observe, measure, and explore the universe. The Hubble Space Telescope, launched in 1990, was the first of its kind of powerful observatory freed from Earth's atmosphere, able to capture deep space images with unprecedented clarity. Over the decades, Hubble has provided some of the most iconic images in science: the pillars of creation, the Hubble Deep Field, the visible cores of galaxies billions of light years away. It helped confirm the accelerating expansion, mapped the structure of the universe, and gave humanity its first real glimpse into the depths of cosmic history. And yet, even Hubble had its limits. Enter the James Webb Space Telescope, JWST, launched in late 2021 after decades of development and delay. Designed to see in the infrared spectrum, JWST can observe light that has been stretched by billions of years of cosmic expansion, light from the earliest stars and galaxies. With its enormous sunshield and precisely aligned mirrors, JWST began transmitting data that stunned the scientific community. Within weeks, it captured images of galaxies so distant, so old, and so unexpectedly structured that existing models of galactic formation were brought into question. It found galaxies that appeared too massive and too well-formed to have evolved in such a short time after the Big Bang, forcing scientists to re-examine assumptions about the early universe. Some theorists speculated that our models of dark matter, or of cosmic inflation, might need to be revised. Others suggested that we had entered a new era, one in which observations would again outpace theory, just as they had during the revolution that followed Hubble's discovery of the expanding universe. Technological advancement did not stop with JWST. Earth-based telescopes equipped with adaptive optics, like those in Chile's Atacama Desert, now rival or surpass the resolution of space-based observatories. The Event Horizon Telescope, a global network of radio telescopes, provided the first image of a black hole's event horizon in 2019, confirming predictions of general relativity in a regime of extreme gravity. The Vera Rubin Observatory, set to come online soon, will map the entire sky with unprecedented depth and frequency, helping to track transient phenomena and potentially illuminating the behavior of dark energy. At the same time, particle physicists at CERN and other laboratories are attempting to uncover the particles that might compose dark matter, with experiments designed to detect rare interactions or subtle anomalies in particle behavior. But it is not just about seeing deeper or building bigger instruments. The turning point is intellectual as much as it is technological. With each new observation, the universe reveals that it is not only larger than we thought, but fundamentally different. The early assumption that the universe is homogeneous and isotropic, that it looks the same in all directions and locations, still holds as a useful approximation, but is now challenged by subtle anisotropies and irregularities in the cosmic microwave background. The notion that space is a passive stage on which matter moves is increasingly replaced by the idea that space itself is active, dynamic, and shaped by quantum fluctuations. The idea that time flows in one direction is being challenged by models in which time may be an emergent phenomenon, not fundamental. The reality we inhabit is not the tidy mechanical system imagined by 19th century scientists, but a seething, evolving, probabilistic sea of energy, fields, and information. This turning point is also one of humility. With the discovery of dark energy and the rise of new observational evidence, it has become clear that we are only beginning to grasp the true nature of the cosmos. The standard model of cosmology, the 195, which includes dark energy, lambda, and cold dark matter, CDM, is extraordinarily successful at explaining a wide range of observations, but it leaves fundamental questions unanswered. What is the nature of dark energy? What exactly is dark matter? Why is the universe flat on large scales? Why do physical constants have the values they do? Are they fixed? Or could they vary in space or time? The answers to these questions may require physics beyond what we currently know, perhaps a quantum theory of gravity, a better understanding of the vacuum, or even a complete revision of our notions of space and time. And so we stand at the edge of an intellectual horizon, pushed there by instruments we have built, guided by theories we have refined, but also driven by a deeper need to understand where we come from, what the universe is made of, and where it is going. The turning point is not just a change in knowledge, it is a change in attitude. We no longer see the universe as a completed puzzle to be solved, but as a living process, a story still being written, with new chapters waiting just beyond our current reach. The tension between what we know and what we don't is not a sign of failure, it is the essence of science. It means we are asking better questions. It means we are paying attention. It means that the cosmos, in all its silence and scale, is speaking, and we are finally learning how to listen. In this era of accelerated expansion, both cosmic and intellectual, we may never again have the luxury of thinking we understand it all. And perhaps that is the greatest gift of the turning point, the reminder that we are part of something so vast, so mysterious, and so beautiful that every discovery only deepens the mystery. The more we learn, the more we realize how much we have yet to learn. The edge is not where the universe ends. It is where understanding begins. And we are closer than ever not to a final answer, but to a new kind of awareness, a new phase in the story of human thought, shaped by the light of stars, the force of dark energy, and the quiet determination to know. What if everything we know about space, time, and reality itself is built on a misunderstanding, not because we were wrong, but because we were looking from the wrong perspective? Science thrives on evidence and logic, but it also depends on perspective, on the framework through which we interpret data. Throughout history, scientific revolutions have been driven not only by new observations, but by changes in how we see those observations. When Copernicus proposed that the Earth revolved around the Sunday, he didn't just shift planetary position, she shifted humanity's place in the cosmos. When Einstein reimagined gravity as a curvature of space-time rather than a force, he redefined the structure of reality. Today, standing at the edge of known physics, cosmologists are beginning to ask whether our entire approach to understanding the universe needs a similar transformation. Could it be that we're asking the wrong questions? That we're trapped by assumptions so deeply rooted, we don't even notice them? Could space itself be an illusion? Time a consequence of entanglement? The universe not a three-dimensional object expanding through space, but a holographic projection of information stored on a distant boundary? These are not wild science fiction speculations. They are serious proposals arising from the tension between quantum mechanics and general relativity. And they suggest that the universe may not be what it seems. One of the most provocative of these proposals is the holographic principle, an idea that emerged from the study of black holes and now influences the deepest questions in theoretical physics. In the 1970s, physicist Jacob Bekenstein and later Stephen Hawking showed that black holes have entropy, that is, they store information, and that their entropy is proportional not to their volume, as one might expect, but to the surface area of their event horizon. This was profoundly counterintuitive. It suggested that the information content of a region of space might be encoded not in the space itself, but on its boundary. In the 1990s, Leonard Susskind and Gerard Tufte extended this idea, proposing that the entire universe could be described as a two-dimensional information structure painted on the cosmological horizon, with the three-dimensional world we experience emerging as a projection just like a hologram. This does not mean the universe is fake or illusory in the everyday sense. Rather, it implies that space and gravity themselves are emergent phenomena, arising from more fundamental processes at a deeper level of physics. If this principle is true, it turns our understanding inside out. We think of ourselves as living inside a vast, expanding three-dimensional cosmos. But in the holographic view, that volume may be a derived construct, like a shadow cast by something more fundamental. Our intuitive notion of space, as a stage on which particles and forces interact, may be just that, a notion. In a holographic universe, locality breaks down. What we perceive as distant points in space might be intimately connected at the boundary level. Entanglement, the spooky action at a distance that so troubled Einstein, becomes not a paradox, but a feature. It is the glue that holds space-time together. And this is where quantum mechanics becomes central to the structure of the universe. Quantum theory has always challenged classical ideas of space and time. It tells us that particles don't have fixed positions until measured, that energy comes in discrete packets, that uncertainty and probability rule at the smallest scales. But more recently, physicists have begun to suspect that quantum entanglement, the phenomenon where particles share information instantaneously across vast distances, might not just be a feature of the microscopic world. It might be the foundation of space itself. According to researchers like Mark van Ramstonk and Juan Maldacena, space-time could emerge from entanglement networks. That is, the geometry of space, the way it stretches, and curvaceous, built from patterns of quantum connections. When entanglement is high, space is smooth and continuous. When it breaks down, space disintegrates. This perspective, called emergent spacetime, flips the traditional order of explanation. Instead of assuming space and time are the stage on which quantum events play out, it suggests that quantum processes give rise to the very stage. Time, too, may be emergent, not a universal clock ticking uniformly throughout the cosmos, but a measure of quantum correlations, a kind of relational property that arises only when systems interact. This challenges one of our most deeply held intuitions, that time flows, that there is a past, present, and future. In some models of quantum gravity, like loop quantum gravity or causal dynamical triangulations, time may be discrete, fragmented into Planck-scale moments that only approximate continuity at large scales. In others, time might not exist at all in the fundamental equations, appearing only as an illusion within certain approximations. This rethinking is not just academic. It has practical implications for how we understand the Big Bang, black holes, and the fate of the universe. Take the black hole information paradox, the question of whether information that falls into a black hole is lost forever, violating the principles of quantum theory. In classical general relativity, the answer is yes. But in quantum mechanics, information must be conserved. For decades, this paradox stymied physicists. But the holographic principle offers a resolution. The information is not lost. It's encoded on the event horizon and slowly released through Hawking radiation, although the mechanism remains a subject of intense research. Similarly, the origin of the universe may not be a point in space, but a phase transition in a more abstract information space, like a change in entanglement structure or quantum coherence. If space-time emerges from entanglement, then the Big Bang could be a moment when the connectivity of quantum systems crossed a threshold, birthing the geometry we now inhabit. The shift in perspective also invites us to reconsider what it means to do science. For centuries, science has been grounded in a realist, reductionist framework. Break things down into parts, measure their behavior, derive laws, predict outcomes. This works spectacularly well in many domains. But in quantum gravity and cosmology, reductionism begins to crack. The parts are not independent. Observations change the system. The observer cannot be separated from the observed. And the deeper we look, the more our tools become entangled with the very phenomena they are designed to probe. This has led some physicists and philosophers to argue for a new paradigm that emphasizes relationality, information, and emergence rather than fixed entities and absolute laws. The universe, in this view, is not a static object, but a dynamic web of interactions, constantly unfolding new levels of structure. One of the most intriguing developments in this shift is the rise of quantum information theory as a foundational tool for physics. Instead of focusing on particles and forces, this approach treats the universe as a computational system, governed by the flow and transformation of information. Concepts like entropy, entanglement, and complexity become central. The laws of physics may not be about things, but about constraints on how information can be processed and transmitted. In this view, the universe is not built from matter or energy, but from bits from qubits, even. And space-time is what happens when those bits are arranged in certain patterns. This connects deeply with digital physics, the idea that reality is fundamentally computational, and aligns with the idea of a holographic universe where all information is encoded on a two-dimensional boundary. These ideas are not without controversy. Many physicists remain skeptical, demanding more concrete predictions and testable consequences. The holographic principle, while mathematically elegant and supported in specific cases like anti-de Sitter, conformal field theory, ADS, CFT, duality, has yet to be fully extended to the universe we actually live in, which is not anti-de Sitter, but de Sitter. Emergent spacetime is compelling, but still largely theoretical. Quantum information approaches raise profound questions, but lack a complete model that can be matched against cosmological data. And yet, even skeptics acknowledge that something must change. The gap between general relativity and quantum mechanics is not going away. The mysteries of dark matter, dark energy, and the cosmological constant remain unresolved. Our traditional tools are not enough. So where do we go from here? First, we must cultivate a willingness to rethink foundational concepts. We must recognize that the conflict between current theories is not a failure of science, but an invitation to evolve. Just as classical mechanics gave way to relativity and quantum theory, so too must our current frameworks yield to something deeper. Second, we must invest in both theory and observation. As technology advances, we may find empirical clues hidden in subtle correlations, in the pattern of cosmic background fluctuations, in the behavior of black holes, or in the statistical properties of quantum systems. New detectors, new algorithms, and new experiments may reveal signs of quantum gravity or holographic effects. Finally, we must embrace uncertainty. The greatest danger is not being wrong is being too attached to being right. Science grows when it questions itself, when it opens to new paradigms, when it listens to the whisper of the unknown. The shift in perspective does not mean abandoning everything we know. General relativity and quantum mechanics are not false. They are approximations, powerful and precise, but incomplete. They are local maps of a terrain that is larger and stranger than we imagined. The new picture that is emerging where space-time is not fundamental, where reality is built from entangled information, where our three-dimensional experience may be a projection challenges our deepest intuitions, but it also offers a more unified, elegant, and potentially transformative understanding of the cosmos, one that honors the complexity of the universe and the creativity of the mind, one that accepts that reality may be less like a machine and more like a network, less like a building and more like a process, less like a thing and more like a question. We are not the first to rethink the universe, but we may be the first to see that thinking itself consciousness, information, relation might be at the heart of what the universe is. And that realization, more than any equation or experiment, may be the true beginning of a new scientific revolution. A revolution not just in knowledge, but in vision. Not just in answers, but in the way we ask. Not just in perspective, but in purpose. It begins, as so many scientific revolutions do, with a contradiction in observation that refuses to fit the model, a pattern that doesn't align with predictions, a question that grows louder as every attempt to silence it fails. For centuries, science has advanced by refining its models, building on known laws, correcting small errors, tightening the fit between theory and reality. But sometimes, a discovery arrives that doesn't merely tweak the equations, it overturns them. It forces a reckoning not only with the model, but with the framework that allowed the model to exist in the first place. In cosmology, this moment came with discoveries that did not just challenge details of our understanding, but the very assumptions underpinning our perception of reality. The expansion of the universe wasn't just continuing, it was accelerating, driven by something we couldn't see or measure directly. Black holes weren't just dead ends. They were thermodynamic engines, information paradoxes wrapped in gravitational singularities. The Big Bang wasn't just the start of space and time, it might have been the birth of an infinite ensemble of universes, each with its own rules. These revelations did not simply modify the map, they questioned the terrain itself. And as more evidence arrived, the unthinkable began to seem plausible. Perhaps our universe is not the only one. Perhaps it is one of many. Perhaps reality is not singular, but plural. The multiverse is not a single theory, but a family of related ideas that arise from different branches of physics. In cosmology, the multiverse emerges naturally from the theory of eternal inflation, a refinement of the original inflationary model, proposed to explain the uniformity of the cosmic microwave background and the large-scale structure of the universe. In this model, inflation never ends everywhere. Instead, while inflation ends in localized regions, like our observable universe, it continues elsewhere, forever spawning new bubble universes with different properties, laws, and constants. Each bubble is causally disconnected from the others, forming an infinite fractal-like ensemble of universa cosmic multiverse. Meanwhile, in string theory, the concept of the landscape suggests that there are perhaps 10 circumflex 500 possible configurations of the extra dimensions and physical constants, each describing a different possible universe. These universes are not just theoretical, they may be realized somewhere in the vastness of the multiverse. From a purely mathematical perspective, this solves several problems. It explains why our universe appears so finely tuned for life, because we live in one of the few universes where life is possible. It removes the need for a unique theory of everything there could be, countless consistent universes, each governed by different variations of fundamental laws. But it also introduces a profound philosophical twist. If there are infinite universes, then anything that can happen does happen, somewhere. There are universes where gravity is stronger, where stars never form, where time flows backward, where civilizations rise and fall in configurations so alien we cannot imagine them. There are universes with no matter at all. There may be universes that have no space, no time, no dimension in the way we understand them. And this idea forces us to confront a staggering truth: our universe may be deeply unremarkable, a typical member of an uncountable ensemble, one bubble in an infinite foam. Yet the multiverse does more than just decentralize our importance, it changes the meaning of explanation. In traditional science, we explain phenomena by tracing causes, deriving predictions, testing hypotheses. But in a multiverse, some features of our universe may be brute facts, not the result of underlying necessity, but of environmental selection. Why does the cosmological constant have its tiny but non-zero value? Why do particles have the masses they do? Why does time move forward? In the multiverse view, these may not be explained at all. They may simply be how things are here. Somewhere else, things are different. This is not ignorance, it's a shift in epistemology. It's a move from deterministic causation to statistical selection. And for some scientists, it's deeply unsettling. It breaks the ideal of a unified, elegant theory of everything. It replaces simplicity with diversity. It makes the universe feel more like a database of possibilities than a structured, knowable system. The discomfort deepens when we entertain the simulation hypothesis, a radical, but increasingly discussed alternative cosmology that suggests our entire universe might be an artificial construct, a simulation running on an advanced intelligence's computational substrate. This idea, popularized by philosopher Nick Bostrom, builds on the increasing plausibility that a sufficiently advanced civilization could simulate entire worlds, perhaps even entire universes, complete with conscious beings. If such simulations are possible, and if intelligent civilizations eventually build them, then there could be vastly more simulated universes than real ones. From a purely probabilistic perspective, this leads to the unsettling conclusion that it is far more likely that we are in a simulation than in the original base reality. Though controversial and untestable in its pure form, the simulation hypothesis reframes fundamental questions. Is the universe digital or analog? Is consciousness emergent or engineered? Are physical laws truly fundamental, or are they computational rules running in a higher substrate? Some physicists point out that our universe does appear to behave in computational ways. At the Planck scale, space-time may be quantized, suggesting a pixelated nature of reality. Entropy and information theory have become central to black hole physics, holography, and thermodynamics. The universe's evolution could be seen as a massive computation, evolving states of energy and matter according to rules. And some studies have even searched for potential glitches in physical constant signs of discreteness or asymmetry that might hint at an underlying code. Whether or not the simulation hypothesis is true, it pushes us to confront a key insight. Our assumptions about fundamental reality may be shaped by our own computational thinking. It urges humility. What we call real may be just one layer in a stack of realities. These developments, the multiverse, the simulation hypothesis, the emergent space-time framework, are not standalone twists. They're part of a broader reorientation in modern physics, a move away from the idea of one cosmos governed by one law and toward a landscape of possible realities, each with their own logic. They demand a new kind of thinking, one that is comfortable with ambiguity, pluralism, and recursion. And they lead us, inevitably, to a deeper question, not just what the universe is, but why we are here to ask. Why should beings like us exist in a universe capable of contemplating itself? Is consciousness a fluke? A side effect of complexity? Or is it something more fundamental? Some physicists and philosophers have begun to explore the idea that consciousness might be woven into the fabric of reality, not as a mystical assertion, but as a scientific hypothesis. Integrated information theory, OR, panpsychism, and quantum consciousness models attempt, in different ways, to account for the emergence of subjective awareness in a universe governed by mathematical laws. If consciousness is fundamental, then perhaps the universe is not a machine, but an experience, not a structure, but a process of knowing. This perspective reframes the twist. The biggest surprise is not that the universe is vast, or that it contains infinite versions of us, or that it may be a simulation. The biggest surprise is that we are aware of it at all, that we can look out into the stars and wonder, that we can invent telescopes, write equations, simulate quantum fields, and imagine alternate realities. And perhaps that is the ultimate unexpected twist. The observer matters. In quantum mechanics, observation affects the system. In cosmology, the anthropic principle suggests that the universe must be compatible with the emergence of observers. In relativity, motion and position are relative to the observer. Again and again, physics tells us that we are not external spectators. We are part of the fabric we are studying. The twist is not in the stars, it is in us. The shift from, "What is the universe?" to, "Why does the universe allow beings who ask what it is?" marks the beginning of a deeper inquiry that blends science with philosophy, physics with metaphysics. So where does this leave us? With more questions than answers, with models that challenge the very idea of truth, with a sense of awe and vertigo, but also with a renewed purpose. The fact that we live in a universe that constantly surprises us, that pushes back against our assumptions, that dares us to think differently, is a gift. Every twist is an invitation not to despair, but to imagine, not to surrender certainty, but to expand possibility. The universe may be infinite, simulated, emergent, entangled, or all of the above. But it is also real, in the most important sense. We are here, in it, asking. And that act of asking may be the most fundamental truth of all. As we stand at the dawn of a new era in cosmology and theoretical physics armed with revelations about the accelerating universe, the enigmatic forces of dark matter and dark energy, and emerging concepts like the multiverse and quantum space-time, it is tempting to feel that we are on the cusp of a final theory, a complete and unified understanding of the cosmos. Yet the more we learn, the more apparent it becomes that some of our most important questions remain unanswered, and new challenges are rapidly emerging. The horizon of discovery continues to recede, revealing the deep complexity and subtlety of the universe. These challenges are not only scientific, but also technological, conceptual, and philosophical. They involve pushing the limits of our instruments, rethinking our theories, and building the infrastructure, intellectual and physical, that future generations will need to continue the search. At the heart of it all is a shared drive, the relentless human desire to know. One of the most immediate and concrete hurdles facing cosmologists and astrophysicists is the limitation of current observational technology. Although telescopes like the Hubble Space Telescope and James Webb Space Telescope, JWST, have expanded our vision to unprecedented distances, reaching galaxies formed within the first few 100 million years after the Big Bang, there are still blind spots in our cosmic vision. We can see far, but not clearly enough. The earliest moments of the universe, specifically the period of cosmic inflation, remain hidden behind the curtain of the cosmic microwave background, CMB. We cannot directly observe anything that happened before roughly 380,000 years after the Big Bang, because the universe was opaque to radiation before that point. The light from earlier epochs simply never reached us. Instead, we rely on indirect signals, such as tiny fluctuations in the CMB or the distribution of matter in the cosmic web, to infer what occurred in those primordial moments. This creates a pressing need for next-generation observational toolstones that can detect even more subtle traces of the early universe and its evolution. Several new projects are already in motion. The Euclid Space Telescope, launched by the European Space Agency, is designed to study dark energy and the geometry of the universe by measuring the shapes and redshifts of billions of galaxies. Its aim is to provide a three-dimensional map of the cosmos that stretches 10 billion light-years deep, helping scientists to understand how structures in the universe evolved over time. Similarly, NASA's Nancy Grace Roman Space Telescope, set to launch later this decade, will investigate cosmic acceleration, dark matter, and exoplanets with unprecedented detail and breadth. But even these missions may not be enough. The deepest mysteries, such as the nature of dark energy, the origin of cosmic inflation, and the fundamental structure of space-time, may require radically new instruments. For instance, to detect the primordial gravitational waves predicted by inflationary models, we would need a space-based gravitational wave observatory like LISA, Laser Interferometer Space Antenna. This mission, planned by ESA and NASA, would detect low-frequency gravitational waves emitted by the earliest and most massive cosmic events. These signals could serve as a soundtrack of the early universe, providing insight into its first fractions of a second. There is also growing interest in detecting 21-centimeter radiation from neutral hydrogen in the early universe. This technique could allow us to map the so-called dark ages of the cosmos before stars and galaxies formed and track the moment of cosmic reionization when the first light sources transformed the intergalactic medium. The Hydrogen Epoch of Reionization Array, HERA, and similar ground-based radio telescopes are attempting to pioneer this field. But the Earth's ionosphere and human radio interference remain major obstacles. A radio telescope array on the Moon's far side, protected from Earth's noise, has been proposed as a solution. Such a project would be ambitious and expensive, but it could open an entirely new window into the early universe. Beyond instrumentation, we face theoretical challenges that stem from the incompatibility between quantum mechanics and general relativity. Both theories are immensely successful in their respective domains, but they fail to work together under extreme conditions such as the singularities inside black holes or the Planck scale physics of the Big Bang. Quantum gravity remains the holy grail of modern physics. With approaches like string theory, loop quantum gravity, and causal set theory, all offering potential frameworks, but none yet able to produce definitive, testable predictions. Bridging this divide will require new mathematics, new paradigms, and new ways of thinking about space, time, and causality. In the meantime, cosmologists must wrestle with several unresolved questions that cast long shadows across the field. One is the nature of dark matter, which has never been directly detected despite decades of laboratory experiments, astrophysical observations, and particle collider searches. If dark matter is made of particles such as WIMPs, weakly interacting massive particles, or axions, then we should eventually find them through direct detection or by observing their interactions in space. But so far, the search has come up empty. This raises the possibility that dark matter is not a particle at all, but rather a sign that our theory of gravity is incomplete. Alternatives like modified Newtonian dynamics, MOND, or emergent gravity remain controversial, but they reflect the broader uncertainty about the true contents of the universe. The question of dark energy is even more mysterious. Is it a cosmological constanta fixed property of space itself? Is it a dynamic field evolving over time? Or is it a sign that general relativity breaks down on large scales? Without a firm theoretical or experimental understanding, we are left with a placeholder in observation with no clear cause. Solving the mystery of dark energy could reshape not just cosmology, but all of fundamental physics. Another major challenge is determining the true shape, size, and topology of the universe. We assume that space is flat, infinite, and homogeneous on large scales, but these are approximations. The real universe may be curved, finite, or even multiply connected, meaning that it loops back on itself in strange ways. Finding out requires exquisitely precise measurements of the CMB, galaxy distributions, and gravitational lensing. It may also require bold new theories about how the universe is embedded in higher dimensional space, as suggested by brane-world models in string theory. To tackle these challenges, scientists are adopting new strategies. One is the increasing use of artificial intelligence and machine learning to analyze the vast amounts of data produced by sky surveys and simulations. These tools can identify patterns, anomalies, and correlations that human analysts might miss, and they can help optimize experimental design, target selection, and theoretical model testing. Another is the growing emphasis on interdisciplinary collaboration, bringing together physicists, mathematicians, computer scientists, engineers, and philosophers to tackle complex questions from multiple angles. This kind of convergence is not just helpful, it may be essential, given the scale and depth of the problems. There is also a push toward open science sharing data, software, and methods across institutions and countries to accelerate discovery and avoid duplication. Cosmology is increasingly becoming a global enterprise, with international missions, global telescope arrays, and collaborative networks driving progress. This reflects a deeper truth. The universe belongs to no single nation, culture, or generation. It is the common heritage of all sentient beings capable of contemplating it. But perhaps the greatest challenge of all is conceptual. Are we prepared to accept what the universe is trying to tell us? That it may be infinite, uncentered, and uncaused? That we are not necessarily special or central? That the laws of physics might be environmental rather than absolute? That time and space themselves may be emergent from something even deeper and more abstract? These are not just technical questions. They are existential questions, and they require a new kind of thinking, one that is open to mystery, comfortable with ambiguity, and willing to question the very foundations of knowledge. This is the future of cosmology. Not just better data or faster computers, but new visions of reality. We must be willing to look beyond our models, our categories, and our inherited assumptions. We must be ready to invent new mathematics, imagine new physics, and pursue ideas that seem strange or implausible. For the history of science shows again and again that progress comes not just from answers, but from the courage to ask better questions. And yet, despite the challenges, there is hope. The very fact that we can ask these questions and build the tools to explore Themis itself, a miracle. The fact that we have peered back almost to the beginning of time, traced the expansion of space, mapped billions of galaxies, and glimpsed the whisper of quantum gravity, all of this speaks to the power of human curiosity and creativity. The path ahead will not be easy. There will be false starts, blind alleys, and failed experiments. But the journey is worth it, because with each new insight, each new observation, we move closer to something extraordinary, not a final answer perhaps, but a deeper understanding of our place in the cosmos. We are explorers, not of lands or oceans, but of reality itself. And our map is unfinished. Our instruments are crude. Our theories are incomplete. But the stars are calling, and the silence between them is full of meaning. The next chapter is unwritten. The next leap has yet to be imagined. And the future of cosmology of science belongs to those who dare to ask and keep asking, even when the universe offers only silence in return. Because in that silence, in that challenge, in that vast unanswered question, we find not just the universe, we find ourselves. The pursuit of a unified understanding of the cosmos has brought science to its most thrilling and precarious precipice. After centuries of mapping the stars, formulating laws of motion, discovering relativity, and unraveling the strange logic of quantum mechanics, humanity stands at the threshold of the unknown, engaged in what may be the final confrontation not against an enemy, but against the limitations of our own knowledge, against the contradictions that arise when our most successful theories collide. At stake is more than just a model of the universe. It is the possibility of finding a theory that explains everything, that answers the deepest questions of existence. What is space? What is time? What is reality? The front lines of this confrontation are occupied by the latest competing theories, each promising to reconcile the great schism between general relativity and quantum mechanics, yet none able to deliver a complete, testable, and widely accepted solution. On one side stands string theory, an ambitious framework that suggests the fundamental building blocks of the universe are not particles but tiny, vibrating strings existing in a 10 or 11-dimensional space. String theory's strength lies in its mathematical elegance and its ability to incorporate gravity naturally within a quantum framework. It offers a rich structure of dualities and unifying principles, suggesting that many disparate physical theories are just different aspects of a deeper reality. It has even led to the holographic principle, a radical idea proposing that everything within a volume of space can be described by information encoded on its boundary. But string theory also has weaknesses. Chief among them is its lack of experimental confirmation. It predicts a vast landscape of possible universes, perhaps 10 circumflex 500 of them each, with different physical constants and laws. While this multiplicity can help explain the apparent fine-tuning of our own universe, it also weakens string theory's predictive power. If anything is possible, what is probable? Without a mechanism to select among these universes or to test them empirically, string theory risks becoming a kind of mathematical metaphysics, beautiful, but beyond the reach of science. Opposing string theory is loop quantum gravity, LQG, which attempts to quantize space-time itself without introducing additional dimensions or assuming a pre-existing background. In LQG, Space is composed of tiny, discrete units called spin networks, and time may emerge from the interactions of these quantum bits of geometry. LQG has the advantage of being background independent and directly focused on resolving the singularities of black holes and the Big Bang. It predicts that space-time is fundamentally granular, that the fabric of reality has a smallest possible scale, yet it too faces challenges. LQG has struggled to unify with the standard model of particle physics and to make concrete, testable predictions beyond what we already observe. These two rival frameworks, string theory and loop quantum gravity, are not the only contenders. Other approaches are gaining traction, such as asymptotically safe gravity, causal set theory, emergent gravity, and entropic gravity. Each presents a different vision of how gravity and quantum mechanics might be reconciled. Some suggest that space-time is not fundamental at all, but emergent from more basic principles like information, entropy, or entanglement. Others argue that the very notion of a universe as a self-contained system may be outdated, and that we should be thinking instead in terms of processes, interactions, and networks. This diversity of approaches reflects a deeper problem. Our fundamental concepts may be flawed. We assume that time is continuous, that space is smooth, that cause precedes effect, and that reality is composed of things rather than relations. But these assumptions are rooted in human perception, not in nature. The more we probe the quantum world, the more these intuitions unravel. Particles exist in superpositions. Events are non-local. Time is not a universal backdrop, but a parameter that behaves differently for different observers. The attempt to unify physics forces us to rethink the foundations of logic, mathematics, and ontology itself. And yet, the confrontation is not only theoretical, it is also driven by observational breakthroughs that continue to challenge our models. The accelerating expansion of the universe, driven by an unknown force called dark energy, suggests that our current understanding of gravity is incomplete. The nature of dark matter remains elusive, despite decades of effort. Observations from the James Webb Space Telescope, JWST, have revealed early galaxies that appear more massive and evolved than standard models predict, raising questions about the timing and mechanisms of galaxy formation. Gravitational wave observatories have opened a new window into the universe, allowing us to detect black hole mergers and probe the nature of extreme gravity. Yet even these triumphs remind us how much we do not know. We are watching shadows flicker on the cave wall, trying to infer the shapes that cast them. The central question, however, remains as haunting as it is unresolved. Will we ever find a true boundary? Is there a final limit to what can be known? Does the universe have an edge either in space, time, or in explanation? Some physicists argue that we may be reaching the limits of empiricism. The multiverse, if real, may be forever beyond our ability to observe or test. The Planck scale, where quantum gravity becomes significant, is too far beyond our current technological reach to probe directly. And yet, others believe that new principles, new mathematics, or unexpected phenomena may reveal pathways we cannot yet imagine. The debate over boundaries is more than scientific, it is philosophical. It forces us to confront the nature of knowledge itself. Is the universe fundamentally comprehensible, as Einstein believed? Or is it an infinite tapestry of mysteries, with some truths forever beyond our grasp? If there is no boundary, then every answer leads to a new question, every theory to a deeper layer. In such a reality, science becomes not a search for final answers, but a process of perpetual becoming, a conversation between the mind and the cosmos, endlessly unfolding. Despite the tension, the attempt to unify physics continues. It is the most ambitious project in science, and perhaps the most difficult ever undertaken. Yet it is also the most necessary. Without a unified theory, we cannot fully understand black holes, the Big Bang, or the ultimate fate of the universe. Without it, we cannot resolve the paradoxes that threaten the coherence of our most successful theories. But to achieve it, we may need to sacrifice cherished beliefs. The division between matter and energy, the distinction between observer and observed, the idea of locality, even the notion of reality as a static set of objects. Many researchers are now focusing on information as the true substrate of reality. From the holographic principle to quantum information theory, The trend is to see particles, fields, and even space-time itself as emergent phenomena arising from deeper patterns of entanglement and computation. The universe, in this view, is not a thing but a process, self-organizing flow of information that gives rise to the appearance of space, time, and matter. This perspective aligns with the rise of quantum computing, entropic gravity, and tensor networks as tools not just for modeling physical systems, but for understanding the universe at a fundamental level. So, what is the future of cosmology? It is likely to be more interdisciplinary, more abstract, and more data-driven than ever before. New missions like the Nancy Grace Roman Telescope, LISA, and CMBS-4 will provide unprecedented precision in mapping cosmic structures, detecting gravitational waves, and probing the earliest moments of the universe. Advances in machine learning and AI will accelerate the analysis of vast datasets and perhaps reveal patterns no human could see. Theoretical physics will continue to explore radical ideas, from loop quantum cosmology to non-commutative geometry to emergent space-time models. And philosophers of science will increasingly be called upon to help interpret the implications of these ideas, to guide us through the conceptual labyrinths they create. But more than that, the future of cosmology will be shaped by a shift in mindset. We will need to let go of the dream of finality and embrace a new vision of science as a quest for the ultimate answer, but as a dialogue with a universe that is always more than we imagined. We will need to accept that the cosmos is not a problem to be solved, but a mystery to be lived. And in doing so, we may find a deeper form of understanding not in equations alone, but in the humility, wonder, and courage it takes to keep asking, even when the answer is silence. In the end, the final confrontation may not end with victory or defeat. It may end with transformation, a transformation of physics, of thought, of ourselves. For as we strive to unify the laws of nature, we are also unifying something within us, the fragmented parts of our intellect, our creativity, our yearning to know. The universe may never give us a boundary, but it has given us something greater, the capacity to search, to wonder, and to change. And that perhaps is the ultimate theory of everything. Not a formula, but a journey. Not a destination, but a becoming. Not a final truth, but a way of being in the cosmos, awake, curious, and unafraid. From the moment early humans first lifted their eyes to the stars and etched constellations onto cave walls, something ancient and profound has stirred within us, something beyond survival, beyond instinct, beyond utility. It is the impulse to understand, to reach, to wonder, to look at the vast silent night and ask questions that have no immediate answers. This act of questioning, of pursuing what lies beyond our current knowledge, is not merely a scientific endeavor. It is a moral one. The exploration of the unknown, especially on the cosmic scale, challenges us not only to expand our intellect, but to grow as a species. It reveals the best parts of humanity, our capacity for curiosity, imagination, humility, and awe, and offers a vision of what we might become if we continue to follow that path. At its core, the moral takeaway from cosmic exploration is this: the universe does not need to be understood, yet we choose to try. And in that choice, we define ourselves. The galaxies will spin, the stars will burn, and time will flow with or without our awareness. But when we choose to study the universe, to launch telescopes into space, to build particle colliders, to simulate the birth of the cosmos, are doing more than collecting data. We are affirming a belief that knowledge matters, that truth, even when unreachable, is worth pursuing, that the unknown is not a threat to be feared, but a horizon to be met with courage. This moral vision begins with curiosity, the engine of all progress. Curiosity is not just a mental itch, it is the bridge between ignorance and insight. It is the quiet voice that asks, why? And keeps asking, even in the face of silence. Scientific breakthroughs, whether in cosmology, biology, or quantum physics, are not born out of necessity alone, but from the audacity to question what others accept. The theory of relativity began as a thought experiment about a boy riding a beam of light. Quantum mechanics emerged from puzzling anomalies in blackbody radiation and atomic spectra. The discovery of the expanding universe came not from dogma, but from astronomers willing to challenge a static cosmos. Time and again, it is curiosity, not certainty, that has propelled us forward. And yet, curiosity is not easy. To explore the unknown is to embrace discomfort. It means letting go of certainty, opening ourselves to paradox, and living with questions that may never be answered. The universe is not obligated to make sense in human terms. It is not required to conform to our preferences or intuitions. When we peer into the deep cosmos and encounter dark matter, dark energy, multiverses, quantum foam, and the possibility of emergent spacetime, we are confronted with realities that defy logic, challenge language, and mock our expectations. It is tempting to turn away, to retreat into simplistic answers or familiar myths. But science asks us to do the opposite: stay open, to remain unsettled, to follow the questions wherever they lead. This is not just an intellectual act, it is a moral one. It requires humility, patience, and a deep respect for the mystery of existence. In that mystery lies a powerful lesson. We are small, but we are not insignificant. The cosmos does not revolve around us. We are not at the center of the galaxy, or the universe, or even of biological life. And yet, we are the only known beings capable of reflecting on that fact. We are made of the same elements as stars, forged in the furnaces of supernovae. The calcium in our bones, the iron in our blood, the carbon in our cell solid, once drifted through space as cosmic dust before becoming part of a living, thinking creature capable of asking where it came from. That is not a diminishment of humanity. It is an exaltation. It means we belong. We are not outsiders in a hostile universe. We are the universe becoming aware of itself. And in that awareness lies purpose not imposed from above, but discovered from within. Cosmic exploration also teaches us about limits and how to live with them. There are things we may never know. We may never see beyond the observable universe. We may never understand what happened before the Big Bang. We may never unify general relativity and quantum mechanics. But the pursuit remains worthy, not because it promises a final answer, but because it cultivates the qualities that make us human: perseverance, creativity, collaboration. In a time when we are surrounded by noise, distraction, and division, the universe offers a kind of stillness, a reminder of scale, a sense of perspective. It tells us that many of the things we fight over, land, politics, ideology, are vanishingly small on the cosmic stage. It invites us to look up, not just in wonder, but in solidarity. For the challenges we face on Earth: climate change, inequality, we're not separate from our cosmic journey. They are part of it. The same curiosity that drives us to study distant galaxies must also be applied to solving problems here at home. The same humility that comes from seeing Earth as a pale blue dot should inform how we treat the planet and each other. The same longing for meaning that leads us to search the stars must also guide our ethics, our compassion, our sense of responsibility. The universe does not offer moral guidance. It does not dictate values. But it gives us a canvas, vast, beautiful, indifferent, which to write our own story. And it is up to us to decide what that story will be. One of the most powerful moral implications of cosmic exploration is the recognition of shared destiny. We are one species, living on one planet, orbiting one star. The boundaries we draw, national, cultural, religious, are real, but they are also contingent. From the perspective of the stars, we are united by biology, by physics, by the fragile biosphere that sustains us. Space exploration, when done with vision and cooperation, reminds us of this unity. The image of Earth from space, a single, glowing orb without borders, has become a symbol not just of scientific achievement, but of planetary consciousness. It invites us to think in terms of generations, ecosystems, civilizational arcs. It asks us to be stewards, not just inhabitants. Yet, even as we reach outward, the universe gives us something else: a mirror. In studying the cosmos, we learn about ourselves, our fears, our hopes, our limitations. The history of science is also a history of human psychology, of the need for control, the desire for certainty, the resistance to change. Every new discovery has forced us to relinquish some comforting illusion, that we are at the center, that we are unique, that the universe is comprehensible, and each time we have had to evolve not just in knowledge but in worldview, in ethics, in maturity. So what is the deeper meaning of exploring the unknown? It is not about conquest. It is not about escaping Earth or playing God. It is about becoming more fully ourselves, about activating the parts of our mind and spirit that lie dormant when we settle for easy answers. It is about cultivating reverence without dogma, awe without superstition. It is about engaging with the mystery of existence, not with fear, but with wonder. In that sense, science becomes not just a method, but a moral pathway of being that values truth over comfort, questions over certainties, humility over hubris. It also invites a new definition of progress, not merely technological advancement, not simply the accumulation of data or the development of faster tools, but the expansion of consciousness, the growth of empathy, the refinement of our capacity to live wisely. A society that values cosmic exploration must also value education, imagination, freedom of thought. It must encourage children to dream beyond the horizon, to ask big questions, to see science not as a career path, but as a lifelong journey. It must fund curiosity, not just for profit or defense, but for the enrichment of the human spirit. And perhaps the most important moral takeaway is this: we are not finished. We are not a completed species. We are still in the early chapters of our story. The universe is 13.8 billion years old. Our species is barely 300,000. The stars will burn for billions more. What will we do with that time? Will we retreat into ourselves, or will we rise to the occasion? Will we use our knowledge to build walls or bridges, to dominate or to understand? The unknown awaits. It always will. And in choosing to face it, we shape the kind of beings we become. The cosmos does not offer comfort. It offers perspective. It reminds us that life is rare, fragile, and infinitely precious. That knowledge is hard-won and always incomplete. That wonder is not a childish feeling, but a courageous stance in the face of mystery. In the end, the stars will not tell us what to do, but they will keep shining. They will keep whispering the ancient invitation: come see, come ask, come learn. And if we answer that call not with arrogance, but with awe, we honor not only the universe, but the best of ourselves. In the vastness of space, under the quiet pulse of distant stars and the eerie glow of faraway galaxies, we find ourselves asking, should the mystery remain open-ended? Should we accept that some answers may forever elude us? That some boundaries may never be drawn? That perhaps the universe itself was never meant to be fully understood? These questions are not signs of resignation. They are signs of maturity. They reflect the evolution of a species that has moved from seeking control to seeking meaning, from needing certainties to embracing wonder. In every field of knowledge, there comes a point when the questions outpace the answers, when the pursuit becomes as significant as the discovery. In cosmology, we are well past that point. We have learned so much about the origins of space and time, the strange behavior of quantum fields, the accelerating expansion of the cosmos, but each new revelation has unfolded more layers of complexity. The deeper we look, the more the universe seems to whisper, "You are only just beginning." To leave the mystery open-ended is not to give up, it is to recognize that the cosmos may not conform to our desire for neat conclusions. Unlike stories, the universe may not offer closure. There may be no final theory, no last equation, no ultimate truth waiting at the end of our inquiries. Instead, there may be only deeper questions, unfolding infinitely like the universe itself. And that, in many ways, is more beautiful. For if everything were answered, if all was known, then curiosity would die, wonder would fade. The drive to learn, to explore, to imagine these uniquely human qualities would have no frontier to push against. But the open mystery ensures that the story of discovery is never over. It gives future generations the opportunity to contribute, to question, to take their place in the unfolding epic of cosmic understanding. Throughout this journey, several core takeaways emerge. First and foremost is the scale of our ignorance. Despite the power of our telescopes and the depth of our theories, we still do not know what most of the universe is made of. Dark matter and dark energy comprise 95% of the cosmos, and yet they remain hidden, elusive, inferred only through their gravitational effects. The laws of physics, which explain everything from falling apples to colliding galaxies, break down at the edges inside black holes, or at the beginning of time. Our two greatest theories, general relativity and quantum mechanics, refuse to unify. They work perfectly on their own terms, but collapse into paradox when brought together. We also confront the limitations of observation. We can only see so far, because light travels at a finite speed, and the universe has a finite age. Beyond the cosmic horizon, there may be countless other galaxies, even other universes, but we will never reach them. This is not just a technical problem, it is a fundamental boundary of knowledge. The universe, vast as it is, may hide far more than it reveals, and we, confined to our tiny planet in one unremarkable galaxy, must accept that most of existence may remain forever out of reach. Yet, even in this humility, we find strength, for we have also discovered profound truths. We know that the universe had a beginning, that it is expanding, that it is filled with structure and order shaped by invisible forces. We have mapped the afterglow of the Big Bang, witnessed black holes collide, and traced the formation of galaxies across billions of years. We have peered so far into space that we are looking into the past, seeing light that began its journey before Earth even existed. We have developed tools like the James Webb Space Telescope, gravitational wave detectors, and neutrino observatories that extend our senses into realms we once thought forever closed. We have built models, LCDM cosmology, quantum field theory, string theory, and more that reveal the astonishing coherence and subtlety of the cosmos. But perhaps the greatest realization is not about the universe, it is about ourselves. Cosmic exploration has taught us that we are not separate from the universe. We are made of its elements, shaped by its laws, sustained by its energy. The atoms in our bodies were forged in stars. The thoughts in our minds are patterns in matter, obeying the same equations as the orbits of planets. We are not outside observers. We are the universe becoming aware of itself. And in that awareness lies a new kind of responsibility. A responsibility to protect the fragile world that allows us to ask these questions. A responsibility to cultivate wonder and knowledge, not for conquest, but for communion. A responsibility to future generations who will inherit not only the earth, but the story we leave behind. So should the mystery remain open? Yes, and gloriously so. Because the open mystery is not a void, it is an invitation. It tells us that we have not yet reached the end of what can be known, that the universe is still whispering secrets, waiting for minds curious enough to listen. It reminds us that science is not a static body of facts, but a living process of conversation between imagination and evidence, between question and exploration. It keeps us humble. It keeps us hopeful. It keeps us human. In this open-endedness, we also rediscover the balance between knowledge and mystery. Knowledge is what we build our equations, our experiments, our models. Mystery is what keeps us building our awe, our questions, our yearning. One without the other leads to imbalance. Pure knowledge without mystery becomes dry, mechanical, complacent. Pure mystery without knowledge becomes superstition, confusion, despair. But together, they create a dynamic tensiona dance between what is known and what is possible. This is the heart of scientific progress. Not the conquest of mystery, but the embrace of it. And finally, we must acknowledge the infinite possibilities of space. Not just the literal vastness of galaxies and stars, but the conceptual space opened by cosmic exploration. The space in which we imagine alternate universes. The space in which we ponder time before time, dimensions beyond dimensions, consciousness as a fundamental aspect of reality. Space is not just out there, it is also within us. It is the space of thought, of vision, of wonder. And as long as we keep exploring both outward into the cosmos and inward into ourselves, the story continues. The future will bring new theories, new missions, new perspectives. We may discover what dark energy really is. We may detect signs of life on other worlds. We may finally unify gravity and quantum theory, or we may find that the universe is stranger than we can ever fully grasp. But either way, the journey will be worth it. Not because we will find all the answers, but because we will continue to ask better questions. Because each step into the unknown deepens our relationship with the cosmos and with ourselves. In the end, the universe may not give us a final chapter, but it gives us something better, an infinite story. One we are all a part of, one we write not with certainty, but with curiosity, not with endings, but with beginnings. And so we look up into the night sky, and we see not just stars, but possibilities. We see not just distance, but connection. We see not just silence, but an open question. What will you discover next? That is the gift of the cosmos. That is the moral of the mystery. And that is the reason we must never stop exploring.